I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students, and just pray that we'd use this time wisely to just cover a little bit more about this topic that we're studying, Lord. In your name I pray. Amen. So, just I wanted to start the discussion about these papers. This is algebrizability, although he has warned me that one of the authors here has warned me that last name Gonzalez or Lopez, at some point I'll learn how to say names. Anyway, he's warned me that they've going with one term and not the other, so this paper's got algebrizability. Well, the other one's got algebrizable. Rest assured, I can't say either. If you get me a little bit tired and or confused or some sort of combination thereof. But anyway, the author I mentioned here, you're a Spanish-speaking student, right? Someone here has taken Spanish, no? Aha! Say how you say that name. Eliphalet? I am quite certain I'm mispronouncing that, which is unfortunate. But also Martin, Eduardo, Frias, Armenta. Anyway, they have some paper that they've submitted somewhere. So I shouldn't say much more about that probably. But anyway, the basic investigation that they're doing studies vector fields. All right, and so you guys know, well, I don't know if you know or not, but if we look at vector fields, right, vector fields on Rn, you know, so what are you doing? You're basically attaching a vector to each point in Rn, you know? So sometimes in calculus we'll look at it something like f, F1, F2, right? Fn, something like that. And so if you really look at it, I suppose if you're studying it from a sort of a manifold theoretic perspective, you might say, well, this is the vector at the point P, and this is an element to the tangent space at P to Rn, right? Like we talked about in advanced calculus and so forth. But suppose you don't do that, right? Suppose you just identify the tangent space at any point in Rn with Rn again, right? Suppose you just say, well, I'm going to say that that's just Rn. I'm not going to be all fancy about it, and I'm just going to look at vectors and identify them with points. Well, from that perspective, the assignment P maps to the vector at P is what? Map on what? It's a map on Rn, right? I mean, for example, we could look at f of x, y, z equal to, 3x, 2y, z. I'll tell you what else I don't want to here. Well, you guys already know, but I'm going to flip the last two. zy, there. So, basically we're saying, well, that's 3x in our usual vector derivation, way of thinking. It would be something like this, right? Identifying E1 with partial x, E2 with partial y, and E3 with partial z. Then we can do things like say, okay, well, that's a vector field, and then we can study integral curves, right? What's an integral curve to this vector field? Would be something like we have f of r of t is equal to what? dr dt, right? This would be the condition for an integral curve. If we evaluate the vector field at the path, then we get back the velocity for the path in this way. So for the example I just gave, this would amount to saying 3x, 3x partial x plus 2z partial y plus y partial z equal to, dr dt. Stupid. Anyway, this is. Anyway, I know I shouldn't be so annoyed. I'm working on it. dz dt, I have several solutions. And then, of course, at time t, but the truth of the matter, this whole thing should be evaluated at r of t, right? So when you sort through this, what this means for these two things to be equal is we have to solve 3x equals to dx dt, right? And we got to solve 2z equal to dy dt. And we've got to solve y equals to dz dt, right? To find the integral curve for my example vector field, we actually have to solve this system of autonomous ODEs. Autonomous in the sense that the differential equation doesn't depend on time, except in the differential sense there. So as I've written it, the left-hand side just involves the dependent variables x, y, z. And of course, this one's simple enough. You guys probably can just straight solve it, right? Like, the first one has solution, x equals to c1 e to the 3t, right? And these last two are coupled, but I would suggest we plug in the third one into the second one. That will give me 2z is equal to z prime prime, right? So therefore z is equal to something like, let's say, c2. I'll write it this way: cosine of the square root of 2t. The square root of 2 is times t, plus c3. An amplitude, you could put a sign there. You could put c1 cosine plus, anyway, something like that. It's that. And then the, of course, y is, what is it? It's minus root 2. Oh, I'm going to make that a sign. Make that a sign. So it's just plus root 2, c2 cosine square root of t plus c3. Of course, you can recognize what we're looking at here, exponential solution, and the sines and cosines go together to parameterize like an ellipse, right? So the integral curve is some kind of, it's kind of neat, right? Can you visualize the integral curve here? Like the x is exponentially growing, right? But these wrap some kind of cylinder, right? Like the so we have so it's some sort of like, I can't do it justice. It's funny though, right? Because it's like they're a little bit dense here. I can't do this. Stink. Eventually I'll learn how to draw these stupid things. Anyway, you get the idea. The point is, it's wound around the cylinder, but the winding gets more and more stretched out as time goes on, right? And as time goes to minus infinity, it just goes to the initial point. Well, as time goes to minus infinity, it seems like the x, I guess it densely winds the, like it winds this ellipse at x equal to c1, right? Like what happens if you keep going back is kind of interesting, right? It gets like that, right? At x equal to c1, yeah? All right, anyway, just refresh in your memory what's a vector field, what are integral curves, all that, right? So what's that have to do with A calculus? Well, the perspective, their perspective is they're interested in a different set of questions, right? I mean, they're very interested in vector fields, studying the geometry of vector fields, studying the differential equations which correspond to vector fields, and all of the various applications of which there are many, right? Attached to, that's the question they're interested in. And so here's their kind of central definition. An autonomous differential equation over an algebra. And so these folks, they like to use the double math blackboard. A for their algebra is denoted, and here it goes, D, oh, I guess it's zeta. Or maybe that's psi. I don't think it's zeta. It's got the 3. Anyway, my inability to write Greek symbols aside, I think it's d xi d tau equal to h of psi. Where h is a mapping from some domain omega, which is a subset of the algebra, to the algebra again. And he does tell us that this is open. So an open subset to keep us out of trouble. And he says that for every point xi naught of omega, a solution to the equation at time tau naught consists of an a-differentiable function on psi, which is going from some neighborhood of tau naught, n of tau naught, which is again a subset of the algebra, to the algebra again, such that what should n of stink here? Zeta of tau naught equals to what? I mean, assuming xi of tau naught equals to what? What do you think? If we plug in the initial tau, we should get the initial xi. And here that's xi naught. All right. Whose a derivative d, my xi's are decaying. Derivative d xi to tau with respect to a. It's kind of a nice language, right? Derivative with respect to the algebra satisfies d xi d tau equal to, of course, h of xi of tau for all tau in the neighborhood of tau naught. He says a theorem of existence and uniqueness of solutions for differential equations over algebras is proved in 16, and a technique for visualization of solutions is given in 5. All right. And you could also make a definition for non-autonomous, but he doesn't do so here. The 5 is a publication by Frias, Martin, Lopez, and Yi on solving systems of autonomous ordinary differential equations by reduction to a variable of an algebra. International Journal of Math and Mathematical Science, I think, 2012. And then the other one he mentions, 16, where the existence and uniqueness theorem is proved, is by E. Lopez Gonzalez, Differential Equations over Algebras, Advances in Applications Math, Sci 8, number 2, 2011. All right. So what do you think? Uh-oh. I should have talked faster. I lost him.
So what differentiates, like,
Oh, you're back.
autonomous? Like, are we referring to some other sort of regular differential equation?
So autonomous, so non-autonomous would be something like D. So it could have a, but I don't know. I mean, like, to me, this is just a first order AODE, where A is, we're using double bar for A. So to me, it looks like a first order AODE, unless I'm missing something here. I mean, he's not using a sneaky notation for like a system of differential equations over the algebra. And we're looking at one differential equation over the algebra. So that's one definition he gives.
So kind of what you're saying, like, this differential equation is not going to be the second, third, fourth order. It's always
Not according to not here. Now that's not the. Just a second, guys. I want to tell you the other definition I wanted to share here. He says definition 2.1. Let A be an algebra. We say that the differential system 1 is A algebrizable if F is A algebrizable. So system 1. Where's system 1? I've lost my system 1. Where'd it go? Oh. Okay, so oh, here it is. It's just right after that. Okay, so this paper exclusively looks at pretty much the following problem, which is x1 dot, in other words, dx1 dt equal to f1 of x1, x2, and y2, come on, x2 rather, dot, in other words, dx2 dt equal to f2 of x1, x2. So this is an autonomous system in the plane in the usual sense. Right? And that's the equation 1 I was referring to just a second ago. All right? And what's a solution to this in the Fréchet sense? It's just a function. What is it? Well, he doesn't say. But I guess we should all know from differential equations anyway, so let me not belabor that point. We know what you mean by solving the system. You find a function, find a path, which is a function of time for x1 and x2, that when you plug it in, it works, right? And it has to, you can pick an initial condition, you find some time interval around your initial time such that the solution exists, and you can give conditions on F1 and F2 to make that unique. I don't think you really need much. Anyway, so, you know, like the, well, anyway, I'm digressing. So if this differential system, let me call this thing 1, all right? If this can be written as a differential equation over an algebra, so suppose you can take this and recast it as an autonomous differential equation over an algebra, right? So suppose you can just look at that and rewrite it as d zeta d psi. Psi? All right, first order of business, I need to learn how to draw that stupid symbol. I keep forgetting to do it. First order. What is the first order? Yeah. So if you can somehow take that and rewrite it as this, in the sense that, and so you're like, what does that mean? In the sense, and here's really where the rubber hits the road, x1t, comma x2t, defined how? Defined as, I should have changed his letter. Stupid psi. Psi of t times e, right? So here, e is what I typically call one sub. It's the one in the algebra, all right? So he says, thus some differential systems having the form 1 can be solved using differential equations over algebras.
What's the point of using the identity thing?
Oh, that's the, I mean, I suppose it's his way of connecting the algebra variable with the real variable t. Like TE is really a restriction of the algebra variable tau. It would be sort of like setting z equal to x times 1. You do a complex calculation, and then you say, to connect with the reals, we're going to set z equal to x. Or to be more specific, it's x times 1. Something like that. Something like that. Now, in this paper, so he gives an example of this, which I could write down. Maybe I will. But then the larger point of the paper is to actually not just, he goes on to look at different kinds of choices for F1 and F2 and describe how you can take the given F1 and F2 and you can create the appropriate algebra from those such that it becomes, that this system 1 becomes an algebrizable, I'll eventually learn how to say this, system with respect to that algebra. Now that to me is very interesting. That's essentially the inverse problem. So this is a problem I don't know how to solve for my A calculus, generally speaking. Let me just kind of, the inverse problem. What is the inverse problem for A calculus? It's something like this. Given a system of PDEs, right? In, say, U1, U2, UN, and x1, x2, xk, right? So these are dependent, these are independent, so you got a system. And even so, I've still not done it justice, because not just one PDE, it's a whole list of them, right? There are a whole list of PDEs and dependent variables, U1 through UN, and independent variables, x1 through xk, right? When is it the case that I can take this system, which I haven't even given you a notation for, right? When can I take this data and somehow recast it as an AODE, or perhaps a system of AODEs? And by AODE, of course, I mean a differential equation over the algebra. By what procedure can I choose an algebra to recognize the given system as in fact being an A algebra, an A calculus problem in disguise. If I had a robust answer to this question, it would make what I'm doing over A calculus all that more interesting, because it would mean that we have a systematic way to discover, frankly, in all likelihood, novel solutions to existing problems which we don't currently have access. I mean, I think those solutions might already exist, but by finding an A calculus representation of them, that would give you a way of understanding them in some sense in a more macroscopic way that would give you deeper insight. In the same way that, you know, you guys experience this in sort of a homework level. In advanced calculus, I sometimes give you a problem. Like, here's this function in real notation, find its inverse. And then you suffer, right? And then you look at my solution and I'm like, this was the cube root function in the complex variable z. So it's like, oh, that's why z cubed was its inverse. Or vice versa, right? So like, just changing to complex notation reveals the true nature of the problem. It seems very possible that there are PDEs out there that are like this, except for the correct choice of algebra. I mean, that's my, I would love for that to actually be something that was non-trivially demonstrated long term. That's one of my long-term goals.
So you're saying the larger problem isn't necessarily like spending the effort to solve the differential equations, it's more of finding a home in which they can't be solved.
Yeah, I think the larger problem is not solving AODEs, it's connecting a given real PDE or system of real PDEs with the appropriate A calculus problem. Solving...
That sounds rather difficult, though, doesn't it? I mean,
Yes, I don't know how to do it. That's the open problem. I mean, I know lots of things that get attached. Like, once I choose an algebra, right? Once I choose an algebra down here, that means solutions that appear in the A calculus necessarily satisfy the A Cauchy-Riemann equations, and then the higher differential consequences of those, which we call the generalized A Laplace equations. Consequently, any kind of whatever this arrow means, it must be such that these original systems are consistent with the generalized Cauchy-Riemann and the higher differential consequences of those. So one of the things the arrow has to suffer is all of the differential consequences. Once you choose an algebra, it comes with lots and lots of baggage, like those differential equations, the algebra, you know, all of those Cauchy-Riemann equations are very, you know, there's a lot to those.
so basically every time I pick an algebra that we can do it, we have to immediately do this test. There's no easy way to just say.
I don't know. Like, here's a, if I was so foolish as to try to say something, like, here's an intuition. If I look at something like, if my given system is uxx, right, minus uyy equals 0, if that's my given system, right, I don't think a complex algebraic simplification is going to work there. Because unless it's some kind, but again, the arrow is very vague what I mean by it, but it seems like any reasonable algebraification of that problem is not going to play nice with complex numbers, because complex numbers require that uxx plus uyy equal to 0. So you put that into the mix, all of a sudden you've forced both the second derivatives with respect to x and y to both be 0, which means all you're left with is linear functions. In contrast, if you make a hyperbolic substitution here, well then hyperbolic substitution gets this for free, right? So if there was extra noise up here, like if I also had ux equal to u squared, that was my system, well then a hyperbolic substitution isn't so bad, because if I make, you know, if I set u, and let's suppose that vy is equal to v squared, just for the sake of, and now I'm probably gotten into trouble, but so if I choose then my algebra to be hyperbolic numbers, right? Then I can try to translate this given pair, you know, into a differential equation of the hyperbolics. What's that look like? Well, I know if I do that, right? For one thing, I know that I've got ux equal to vy. I've got vx equal to uy, right? I mean, I've got the Cauchy-Riemann equations over the hyperbolics. Those are good. And so my original system translates what into really vx equal to v squared, right? And ux equal to u squared, which means if I look at partial x of u plus jy, jv, what do I get? I get u squared plus, jv squared, for what it's worth. And so that becomes the differential equation, dw dz, let's say, equal to, but then you see, I'm still not guaranteed that that's anything nice at the level of hyperbolic notation. I mean, what is u squared plus v squared in terms of hyperbolic variable w? See, w squared is u plus jv squared in my notation here, which is u squared plus v squared plus 2u vj, right? So, I mean, I could look at this. See, I could look at that, and what would this dwdz be useful for me for? It would actually be very useful, because the real part of that solution would solve my original system. And the imaginary, sorry, so stupid, solution to that would solve a corresponding problem involving u and v, right? I mean, so, see, the real part of this is exactly, oh, well, I'm not sure about that. Anyway, I think this is relevant, but I'm actually not sure about that either. But anyway, I'm not trying to do this, okay? I'm just trying to show you the sort of the genesis of the discussion. I mean, I don't know what to do, generally speaking. I have examples which I've worked out. I've worked months and months on this before. And I've gone a long, long way down the path, and I'm not willing to continue at the moment, except to describe the problem to you. Oh, right. Now, the paper that I'm looking at it's not this. They're not interested in this problem. They're interested in something much, much more specific. They're interested in, given an autonomous system, how do you find a two-dimensional algebra where this system becomes a single differential equation in one algebra variable, one dependent algebra variable with respect to one independent algebra variable. See, so a lot of the dimension counting that I'm suffering with over here, like how many dependent, how many independent, how many in the system, am I looking for one differential equation or two? All that stuff is not, all that kind of dimensional ambiguity is gone.
I mean, that's not so bad. Just doing one-dimensional cases, you can kind of then move up to a two-dimensional case.
Exactly. Right. They're smart. They have picked off a bite they can chew. They have more sense than I do, and that's good. But the next paper that I haven't really said anything about actually deals with not just two-dimensional stuff, but some higher dimensional questions. So we'll get back over to that one later. But so King, King. Ah. It's okay. If I had to take some of the classes you're taking right now, I would also be very, very sleepy. Oh, I'm sorry. So I just wanted to make sure before I go on here, do you understand so the basic idea here is for this paper, the first paper, excuse me, the one I'll send you guys, algebraizability of planar vector fields. Planar vector fields. So every planar vector field corresponds to an autonomous, well, as long as the vector field is not time dependent, static vector field, right? It corresponds to a system of autonomous differential equations. This system is said to be algebraizable if this can be recast as a single differential equation over the algebra. And this paper actually gives us conditions on how to build the algebra for reasonable choices of F1 and F2. All right. So that is a good basic example of the inverse problem for them, right? And you can see that it should somehow be related. At the end of the day, it's somehow got to be related to my larger question of the inverse problem. Yeah. This is very nice. This is cool. This is the kind of nice idea to link these two. Should I look at the example that they give in the paper? It might be helpful, I think, just to make sure we draw. And then we'll come back to this paper with the more technical stuff in a future day. I just wanted to try to get the discussion started here. I've read a good bit of the paper, but it's still not, I really need to sit and just calculate everything before it's real to me,
Next question. You said something about the calculation of the uniqueness of the solution.
Yeah.
But is there such a thing as a uniqueness in the algebra? Did you say we could choose multiple algebras in which kind of solution that each
That's a good question. Is if you can find an algebra for which it's algebraizable, to what extent is that unique? What flexibility is there in that construction? I don't know.
I feel like
Or also, is it the case that every autonomous system of differential equations in the plane permits an algebratization? I know the answer to neither of these questions at the moment, but they may both be answered in this paper. So, here's his example, and this is funny because I don't know. This is funny because one of my go-to examples in sort of showing the magic of A calculus as it relates to PDEs has always been this example. And it's not because I've read their papers or something. It's a nice example of the algebra doing something that looks bizarre from the other viewpoint. And so here's the example. Is this system, dx1 dt equal to 3x1 squared. Actually, this example is a little bit more exotic than what I was saying. I'll show you what I was saying once we get through this. Because the other thing I wanted to do today was to try to start the discussion about how to solve differential equations over an algebra, which I have a lot to say there. I have a lot more to say there at the moment. Let's see here. So this is his given system of autonomous differential equations. And he says basically that this amounts to, if you change notation essentially, d zeta d tau equal to zeta squared over, on the algebra A, which is, and then here's where it gets weird. The A is given the following product. So x1, x2. And I'm going to put a star in here, but he just uses juxtaposition. But I'm going to use a star because that's what we've been doing in here a lot. So just so you guys kind of get the same right idea. Product of this and that, by definition, is 3 times x1, y1 plus x1, y2 plus x2. I have no intuition what this is. x2, y1 minus, I'm quite certain it's to illustrate a theorem later in this paper. But beyond that, I don't have a good intuition for what on earth is going on here. 3x2. Now maybe after the dust settles, I'll be like, oh, that's just the blah and blah. But I'm not there yet. So to me, this is just some kind of mysterious formula that's come to us from, Mexico. Let's see your x1. So, good eye. Yes. Wow, you really understand this stuff. Interesting. Let's see here. Now he says, he does not give the mechanics and the, what do you want to say, the yeah, the computational machinery to directly show that this reformulates to that, all right? But what he does, but on the other hand, he says, well, this much we can, I think we've done enough calculus in here over in algebra to say this much, that this permits the following solution, which is what? Well, here, let me show you how we actually, this is informal, but you can look at it like this. This is really d zeta over zeta squared, right? And I said zeta, but I meant, I'm going to change that to a zeta. Because my zeta is also bad, but it's not as bad as the xi. D zeta over zeta squared equals d tau, right? And so if you just formally anti-differentiate both sides here, you get minus 1 over, you know, zeta is equal to tau plus a constant, right? So solving this for zeta gives us minus 1 over a constant plus tau. So this right here, that is boxed, that is the solution